And I'd like to introduce our very own Neil Durans, who is a distinguished presidential appointee here at ETS, and he'll be talking about relating scores and aligning score distributions.
Thank you, Amy. Well, let's see. First time I was in this room, I got some filler because I figured let some people come in for a while here. First time I was in this room was in 1980, April of 1980. 30 years ago. Can you hear me now? Okay, I have to. Yeah, I got to stay close to this thing. Okay, all right, I'll try. As I was saying, the first time I was in this room was in April of 1980. There was a conference on equating, test equating, that was organized by Paul Holland and Donald Rubin. It led to a book on score equating. 10 years later, there was a conference in here, and I was one of the speakers at that conference on differential item functioning, which was organized by Howard Weiner and Paul Holland, and that was kind of an important presentation for me. And so when Amy approached me about talking today, I had to choose between fairness on the one hand and score equating on the other hand. And as you can tell from the title, I chose score equating. The reason for it is basically I'm a score guy more than an item guy, and most of the fairness stuff deals with items. Okay. Now, Paul Holland, who I worked with for many years, said in the late 1980s, 1990s rather, that few wish to assess others, fewer wish to be assessed, but everyone wants to see the scores. So my talk is more about scores than it is about validity of scores or about future directions for how we get scores. But eventually you end up with scores, and you've got to do something with those scores. And I gave a talk recently at the Association for Test Publishers in March, and I said many want to compare scores from different tests. So in particular, I'm going to talk about not only scores and linking scores, but linking scores from different tests. I mentioned Paul Holland. He was, in the late 90s, he was at Berkeley and between stints here at ETS. And he was involved with the National Research Council committee that looked at ways of trying to link test scores to NAEP in particular. And they put out a really good book called Uncommon Measures in 1999. And it had 4 conclusions. And the gist of the 4 conclusions was that you really can't do it. You can't take tests that are from different places and put them all on the same scale, except under very special circumstances. And those circumstances would be the content has to be very similar, the testing conditions have to be very similar, and things like that. Basically, the tests have to be very, very similar to each other before you can do it. And he gave me a copy of the book, and in the book he said, for Neil Durans, who said it couldn't be done, was right. So now, why did I say, did I tell him when he asked me these questions, did I say it wasn't going to be, you couldn't do it? Well, that's because I spent a lot of time, my early time at ETS, working with aligning score distributions. In the 1980s, I equated the SAT for a long period of time. While I equated the SAT, I realized there was a fundamental problem with the SAT scales, in that the math scales had a mean of about 475 on a 200-800 scale, and the verbal scores had a mean of about 425. So there was a 50-point difference between them, and the 425 was considerably below the 500 that everybody thought the average scores were. So we fixed that by recentering the SAT scores. It took me a long time to publish it. The recentering was actually done in the mid-90s, and I published it in 2002. And that recentering work led to a need to do concordance work on ACT and SAT, because the SAT scores distributions had changed, so the ACT had to be linked with the SAT all over again. I worked with Mary Pomerick, who at that time was at ACT, and I've worked with her since on these kinds of issues over the years. And we published a report in colleges and universities on a concordance between the ACT assessment and recentered SAT sum scores. Howard Everson at that time was vice president for research at the College Board, and he said he kept getting calls from all over the place wanting to link SAT scores to everything you could think of, probably including NAEP at that time. And so he asked me to think about coming up with guidelines for when you should concord and when you shouldn't concord. And that led to this College Board report that was published in 1999. And so while I was working on this, Paul was working on that Uncommon Measures book, and when he came back to ETS, we got together and started working on coming up with a framework for linking. And that appeared in the last edition, the most recent edition of Educational Measurement that Bob Brennan edited, and also a lot of what Mike was talking about probably appeared in there too, right? In that same volume. And in that volume, we came up with a framework. I wouldn't say unified framework, but a framework for talking about linking scores and score distributions. And so I'm going to talk about the topology for linking that we put together that was based on other topologies that existed, and talk about different types of scale aligning that occur in the field, what separates equating from other types of scale aligning, and finally, the distinction between predicting a score and making score distributions look comparable. Okay. So everybody wants to link scores from different tests to each other. And there are different ways of doing this, and they're done in different contexts. And so there's a need to kind of organize the various linking procedures and types of linking into a topology. And these topologies actually go back a long ways. In 60 years, people have tried to do this kind of work. And Paul and I put together something where we decided that we would say that there's linking of scores on, or score distributions on X to score distributions on Y falls into 3 subcategories. One is predicting, and there you're focusing on predicting the best score from other scores. Another is equating, where you're making score distributions comparable with the hope that you will achieve interchangeable scores, or at least scores that can be used interchangeably. And then finally, a broader area of scale aligning, which focuses on making score distributions comparable in some population. So this is a figure summarizing what I just said. Predicting, which is what I learned about in graduate school in the 70s. I didn't learn anything about equating, even though my major professor at the University of Illinois was Ledyard Tucker, who did some of the first equating work ever. He didn't teach me that stuff. I learned about that when I came to ETS in the 80s, and the focus of equating is to try to produce scores that can be used interchangeably. And then scale aligning is something I drifted into when I first started to recenter SAT scores. That was a form of scale aligning. I aligned the SAT and verbal scores to each other in a particular reference population. And then there was, then I got into the concordance studies. And there the focus is on producing comparable scales. It's not scores. The scores are not comparable. It's the score distributions that are comparable, and that's an important distinction. So I'm going to talk about the last one first, aligning the scales of 2 test scores. And it's a complex category. It has many subcategories. And you can always think of scores on a test X and the scores on a test Y. For example, weight and height, both of those are measures of size. And you can put them on a common scale. You know, how many sizelets you have or something like that. You could put them on some scale, and you can link them. And you can link them in different populations. You can link them in professional football players. You can link them in professional basketball players. And guess what? Those scalings will not be similar. They'll be very different. And so, but you can do it. You can always do these things. It's very easy to do. Does it make sense? That's a different question. And there's at least 5 factors that Paul and I identified to try to classify scale alignments. One is, how similar is the construct that the tests are measuring? You know, SAT, different editions of the SAT, construct is the same, very similar. SAT math and ACT math, yeah, they do it differently, but they're both getting at math, so they're similar. Height and weight, well, those are more dissimilar, but they're getting at size. So there's the degree to which you have similarity or dissimilarity of the construct you're trying to link the scores from. Then there's a question of how reliable or similar they are in reliability. Are these 2 things that we're linking, do they have similar reliability, or is one more reliable than the other? Another factor is, are the test scores similar in difficulty or dissimilar in difficulty, and are they appropriate for similar or dissimilar populations? Now, Another thing we talked about was where the data comes from. There's two types of data that are used for linking in particular. Data in which there's a common population that takes all the tests, or you have different populations taking different tests and you have some common material, test material, some kind of anchor to connect that stuff. So those are two types of classifications. And we summarize it in this figure here, which comes from that chapter I mentioned before. And in 2005, ETS hosted a conference, a two-day conference on linking and aligning scores and scales. And out of that came a book that I co-edited with Mary Pomerick and Paul Holland on the SID. And that conference was talking about basically the different types of scales, different type of linking scale alignments that you could use, including equating, which does not appear on this table. But as I said before, you have dissimilar constructs versus similar constructs. You can either use common population or an anchor measure to do the linking. You could have dissimilar or similar reliability. If you have dissimilar reliability, we use the term calibration to describe it. It's not the same thing as an IRT calibration. This is like calibrating something that's very accurate with something that's less accurate and putting them on the same scale so they have the same numbers. That numbers have different uncertainty associated with them, so it's not an equating. And then you have something like vertical scaling, which can only be done through an anchor measure because it's given to different populations. You have like fifth graders and third graders. Those are different populations. The fifth grade test is usually more difficult than the third grade test, so you have dissimilar difficulty, and you use an anchor test to do the linking. Then there's the concordance work, like I mentioned before, where you're talking about tests that are close in difficulty, kind of measuring similar constructs, and you can try to link them through, typically done through a common population design, but you could use an anchor measure to do it as well. And then on the far side here, your left, my right, is battery scaling. That's where you have dissimilar constructs. For example, when I recentered the SAT, we had a verbal test and a math test. That's what a verbal test was called, verbal back then. And we put them on the same scale. So that was a form of battery scaling. Okay. All right. I'll skip those two slides because I just described that. And then I'm going to talk about a special kind of scale aligning called equating. And back in 1982, when the Holland and Rubin book came out, it was really one of the first books that came out on test equating. Since then, there have been a lot of work done on it, especially in the 90s and after that. And in fact, I have two people in the audience here, one up front and one in the back, Alina and Skip, who have done quite a bit on this and written books on, I consider Skip's book that he produced to be a book as well, even though it's an ETS report on equating. And then there's the work that's been done by Colin and Brennan a lot. So equating is something that people have spent a lot of time on over the last, during my career, basically the last 38 years or so. Why do we worry about equating? Well, if we have different editions of a test, we want to make sure that it's as best as possible, we can attain a situation where it really doesn't matter which form a test taker takes. I stumbled there because in principle, test content matters and people have differential exposure to test content, so it really does it'll matter even in practice there'll be a difference that occurs because of the nature of the content. But this is talking more from a theoretical point of view, that we're trying to create editions of tests from the same set of blueprints so that a priori we can basically assign any of one of these tests to the person and hopefully end up with the same expected score distribution for that person. And if that happens, then the test can be used interchangeably. Test scores can be used interchangeably. And what we now call linear equating functions and equipercentile equating functions are basically adaptations of methods that have been used for scaling throughout the years as well. Okay. I'm going to skip that because I want to save time. And I'm going to focus on what makes a linking different from, an equating different from other types of linking or other types of scale aligning. Number one, on the similar to dissimilar constructs dimension, the construct has to be the same. You have to be measuring the same thing. Okay? That should be pretty obvious. Number two is a thing called equity, which the equity requirement, which is something that Fred Lord proposed back in 1980, in which he said it should be a matter of indifference to the examinee to be tested by either one of the two tests that have been linked. Again, in practice, you can never achieve this. In practice, you can never really assess this because it assumes you know what the person's ability is. In order to assess strong equity, you have to actually know their ability. But if you knew their ability, you wouldn't have to give them the test in the first place. So you're sort of in this bind where, so what do we do? How do you evaluate equity if you can't evaluate it directly? One way to evaluate it is through the equal reliability requirement. So if tests do not have the same reliability, you can be sure they don't meet the strong equity requirement. This is a very simple thing. This is a requirement that Paul and I added to the requirements that Fred Lord had proposed in his 1980 book. Then there's another testable thing, a population invariance requirement. And this is something that a lot of work was done on starting around 2000 when Paul and I wrote an article in Journal Educational Measurement where we proposed some indices that could be used to assess the population variance of linking functions. And what I mean by that is if you had test X and you had test Y and you would administer to randomly equivalent samples from the same population and you did the equating of X to Y, or the linking of X to Y in that population, and then you broke that population into subpopulations, for example, males and females, and you did the same equating in the males only, or did the same equating in the females only, those three linking functions should look the same. And that's what's meant by population invariance. And as I mentioned, indices have been developed for assessing that, and there are several special issues of journals on this topic. Alina Van Davier was co-editor of one of those, and I was an editor of another one in 2004 for the one I was in, I think 2007 for the other one, but I'm not sure. And this is an area that you can assess it if you have the data. And then finally, there's something that Paul and I originally called a property of equating, and Fred Lord called a requirement of equating. But I actually think of it as something as a property because unlike the others, this one really doesn't depend on the data. This one is something you can make happen. Symmetry is very easy to achieve. You can do it through a mean sigma linking. You can do it through an equipercental linking. And these are characteristics of the procedure, not necessarily of the data. Whereas population variance and same construct and strong equity are characteristics of the data as well. So I decided to call this a property as of this talk, to make it different from a requirement. So this is a procedural property. Okay. Now Mike Colin in a book that came out of that linking conference that I mentioned before had a chapter where he described three features of a testing situation that affect equating. And one is, from a practical point of view, the test content. Content and stat specs, they serve as a blueprint for test construction, and they should be as similar as possible. And they need to be, if you're talking about equating, the tests have to be built to the same blueprint. Another thing that's important is the populations that take tests X and Y. They should be similar to each other, and the test needs to be appropriate for both populations. And finally, conditions of measurement. The conditions of measurement in which they are administered need to be similar, if not identical, or they shouldn't matter. I mean, you have to basically demonstrate that conditions of measurement don't matter. And some of the conditions of measurement that are under control of the test developer are things like the instructions used for the test, like right-scored testing versus some other type of scoring, instructions, the format of the test, the mode of administration, computer-based versus paper and pencil versus, the small device, whatever. There's different types of modes of administration that could could change the conditions of measurement and have an effect on the test scores. And then there are things that are outside the examiner's control, such as the motivation of the test takers. Really, it's hard to control the motivation of the test takers. You might try to do it through incentives, but it's really something that's outside of our control. And things like power outages and stakes associated with the test, things like that. Those are things that are outside of our control. But they are conditions of measurement that need to be attended to. I always view equating as being the pinnacle of scale aligning. And as with any type of scaling procedure, the data can come from a common population or involve an anchor test. But in terms of the scaling diagram that I had before, equating would appear to the right of concordance, and because it would involve identical construct, identical reliability, and identical difficulty, or closest possible difficulty. And I would argue they also need to have high reliability, and you'll see why later. There's several, as I mentioned before, there's several excellent books that have been produced on linking and equating that were not available when I was in grad school, but definitely are out there now. And they go into a lot of detail about what's in this diagram, so I'm going to skip that. And I'm going to talk about the other linking that I hadn't really mentioned before, which is predicting. And predicting is very different from scale aligning. In scale aligning, and equating is a special form of scale aligning, you focus on making the score distributions as comparable to each other as you can, by some definition. In prediction, your goal is you have some criterion that you're interested in predicting, and you want to make the best prediction in terms of reducing your uncertainty about the prediction. So it's a different idea. It's a focus on scores as opposed to score distributions. For example, you might want to predict GRE scores from GRE scores. GRE scores that you had from the past for GRE scores in the future. That's a prediction problem. There are differences between scaling and predicting. For scaling or scale aligning, samples come from a common population or from different populations that take an anchor test. With predicting, they basically, when you're predicting scores, they come from a single group. You need to have the X's and the Y's on the same group to do the regression, to do the prediction. With scaling, you don't have to have that, so that's a distinction. And predicted scores are regressed to the mean, whereas aligned scores are not. And this is one reason why prediction or regression is not a very good equating procedure, because of this regression to the mean phenomenon. So in this diagram here, I have the regression of score y on x, which is the blue line, regression of score x on y, which is the red line, and the scaling function. And if you take a score on the scaling function and go into it, you end up with a score on y. If you go back to that scaling function, you go the opposite direction, you end up with the x that you started with. So scaling functions are invertible in this sense. Regression functions are not. If you go into the regression function for predicting y from x, you'll see a 2 is going to give you something close to a 3. If you then go into the regression function for predicting x from y, you see a 3 is going to give you something higher than 3. So you get this regression to the mean phenomenon. And that's why regression does not work for scaling purposes. Okay. On the other end, and this is another way of describing that, let's assume we have, in fact, two parallel scores, x and y. So we don't have to worry about equating because these scores are already measuring the same thing. They have the same distributions. They have the same relationships with external variables. So they're truly parallel. And they have reliability greater than 0. The standard deviation of the predicted y score from x is going to be r times the standard deviation of y, which was what you see in this picture here. You get a regression towards the mean, which means the variance of the predictions is less than the variance of the thing being predicted. And unless r is equal to 1, correlation between two parallel measures is reliability. Unless that reliability is 1, the standard deviation of the predicted y from x will be less than the standard deviation of y. So this is why predictions do not produce interchangeable scores. Now there's a thing called proportional reduction of mean squared error of prediction. So the idea here is that if you have a distribution of scores on y and you know nothing else and you want to minimize the mean squared error, you know that the thing to use is the mean. That'll minimize your mean squared error, and that mean squared error will be the standard deviations of the score on y. If you have additional information on x, and you want to reduce that mean squared error, and you get a predicted score based on the relationship between y and x, you'll find out that the proportional reduction of mean squared error is equal to r squared. So you're going to reduce the uncertainty about where a person is in that distribution of y by r squared. So if r squared is 1, you reduce it perfectly. You know exactly where they are. If r squared is equal to 0, you're where you were when you started. And so this PRMSE indicates how much value X has for predicting Y in terms of reducing the mean squared error. And the higher the value of R, the greater the proportional reduction of mean squared error relative to the mean Y score. Now, what happens if you are bothered by the fact that your predicted scores have less variance, a lower standard deviation, than the thing you're trying to predict? And you say, I'm going to replace that predicted score with X, because X we know is already equated to Y, it was parallel to Y, and I'm going to use that as a prediction for Y. I'm going to use the X score instead of the best linear predictor. I'm going to use the X score instead. Well, if you do that, you reduce the mean squared error associated with using the mean by 2 times 1 minus R squared. Now, I put reduce in quotes because when R is less than 0.5, this reduction can be negative. So it's not a good reduction, it's a bad reduction. And I call it the proportional change in mean squared error because change can be positive or negative, whereas reduction sort of suggests that you're going in one direction. And so you have this proportional change in mean squared error of 2 times 1 minus R. Graphically, I don't know how well you can see this back there, but with all these lights from outside coming in, what we have here is the line that bends is the proportional mean squared error, reduction in mean squared error for the regression line. And so if the correlation is 0, you end up with 0 reduction in error. So you don't really, X doesn't help you much. As X approaches 1, you get quite a bit of reduction in error. If you start out with a predictor that has 0 correlation with Y, you end up making things much worse by using that than if you just use the mean Y. And so that what this shows is that as your correlations get higher and higher, like 0.9 or higher, these two proportional reductions are very similar to each other. So the scaling is a pretty good predictor of what you're going to do the next time you take the test. As that correlation drops, it becomes a poorer and poorer predictor relative to the mean score. And when it falls below 0.5, it gets worse than using the mean score. So, comparable score distributions produce neither interchangeable scores nor perfect predictions unless both scores are equatable, that's measuring the same thing in the same way, and perfectly reliable. This is really goes beyond what Lord said in 1980 in his famous, he said, equating is either impossible or unnecessary. This goes beyond that. It says that you need to have basically parallel or infallible measures in order for you to have observed scores that are perfect predictors of their parallel scores. And there's two articles I'd like to point you in the direction of, one by Paul Holland and McDell Hoskins. It appeared in Psychometrica in 2003. The ETS research report you can get from 0220. And Bob Brennan has a CASMA report, number 30, both of which show that high reliability is really important for subpopulation invariance in the case of Holland and Hoskins, and for strong equity in the case of Brennan's paper. So these point out that high reliability is important. So in sum, I talked about topology of linking, some types of scale aligning, equating requirements, predicting, and saying that expected scores and comparable score distributions are not the same thing. They can't be used for interchangeable reasons. And I did this because there's an awful lot of scale alignment going on in the field, and I think there's too much of it going on, and we need to step back and realize that these scale alignments, like concordance studies, are not the same thing as equatings. They're not producing sets of scores that can be used interchangeably. And they often produce poor predictions. If you're interested in predicting, say, ACT from the SAT, you do a better job with a prediction equation than you would with a concordance. And fortunately, as reliability increases, the differences between these things get smaller and smaller, and the equated scores and the predicted scores converge. And I believe that may be the end of my talk. So I'd like to, I have something I want to say at the bottom of my notes, which I forgot because I'm getting old.
You're distinguished.
Yeah, something like that. If you want to mitigate the effects of a particular test form that a candidate takes, then equate tests that are built to the same specifications. If you want to know how well a test taker is likely to produce on a parallel version of the test they already took, then probably you want to get a prediction for that purpose. So those are the final points. And I guess I want to say is it's important that you think about the data that you have, the tests that you have, and that you don't just be a data monkey, which is basically taking data and sticking it into programs and getting out results. So thank you.